So please confirm me, is it visible?
Yes, it is visible.
So the topic name is structural analysis using energy methods. So first of all, the question comes in mind, why should we use energy methods for structural analysis? Because these are typically little bit difficult rather than the normal methods. So the energy methods are generally used when there is statically indeterminate structures, because if there is a determinate structures, then it can be easily solved by the force equilibrium conditions as well as the compatibility equations. But when there is statically indeterminate structures, then we need the energy methods. By using these energy method, we integrate our equations and find a solution. So analysis of structure is possible in some instances based on static equilibrium equation only. Such systems are generally called as statically determinate structures. So what it means that the if we can solve the equation of structure by just static equilibrium equations, then the structure is known as statically determinate structure. First of all, what is static equilibrium equation? A static equilibrium equation is uh, that we can say the for summation of forces in x direction is equal to 0, summation of forces in y direction equal to 0, and summation of forces in z direction equal to 0. These are the static equilibrium equations. By doing these equations equal to 0 in any structure, and we are getting all the unknowns, then we can say that structure is statically determinate. Now, many structural systems require the knowledge of deflection of individual elements in addition to the static equilibrium equation for the analysis. Such equations are known as statically indeterminate equation. So, what is the difference between the statically determinate and indeterminate equation? That we need to have a knowledge of deflection of individual elements as a additional equations to determine all the unknowns. It means that in determinate structures, we need to get the static equilibrium equation first. Then we also need to have a knowledge of deflections of individual elements. By clubbing these two equations, first is static equilibrium equation, second is deflection of individual element, we can solve the statically indeterminate structures. One way of analyzing statically indeterminate structures is known as using energy methods. When the energy method comes, the Castigliano gives his theorems regarding the energy methods. To how to solve these energy methods, the Castigliano gives his theorems. Later on, we will discuss about what the theorems that Castigliano gives. So in this equation, this is first of all, this is our first problem. What is seeing it? It is a rod of length L, area A, is subjected to an axial force F, and it is hinged at the top section. Now, when it is pulled by a force equal to F, then there will be some deflection. We call the deflection equal to delta. Now, how we will determine the deflection? We can say that it is an axial force acting on the member of length L and area A. The value of axial force is F. So the deflection delta produced by that axial force is equal to FL upon AE, that we have studied in solid mechanics courses or as well as in structural analysis courses. Now, the second case. In this case scenario, there are two members. First, with area A1, length L1. Second, with area A2, length L2. The force is acting at the joint of member 1 and member 2 in the downward direction. The value of that force is F. Now, the first question should be comes in mind that where will the structure will deflect? Where this will structure will go? If the force is pulling in the downward direction, that both the structures will start moving downward. Now, this structure will go in this side little much, and this structure will go this side. So we will have a So we will have a horizontal displacement that is called as delta x, and we will have a vertical displacement that is known as delta y. Now, how we will solve this system of equation? Now we can say that the force in member this one, let we can say is F1, and force in this member second we can say is F2. Here better graphical representation is given. Force is given F1. Second member force is given F2. The bottom force, the given force is F. We have assumed the force F1, the member 1 is inclined to horizontal at an angle of theta. Member 2 is inclined with horizontal at an angle of alpha. Now, we can easily find out we need to find out the value of F1 and F2, because if we get the values of F1 and F2, we will easily get the forces in these two members. Now, what is we can do? Now, I have already explained you previously. Now, to solve the statically determinate equation, we need to find out static equilibrium equation. So, what is the static equilibrium equation? First, we can do is sigma summation of forces in x direction equal to 0. What will be the forces? F1 cos theta minus F2 cos alpha is equal to 0. This is the first equation. We have two unknowns, so we need to determine two equations of equilibrium, and we can easily find these two unknowns. So first equation is sigma fx equal to 0. Second equation is sigma fy equal to 0. What will become? We can get the forces component in vertical directions. And the force of F1 in vertical direction is F1 sine theta. The vertical direction or vertical component of force F2 is F2 cos alpha, sine alpha. That should be equal to force F. That is F1 sine theta plus F2 sine alpha should be equal to F. Now, what we have? We have two equation of equilibrium and we have two unknowns. So we can easily solve these two equations and we will find out the value of F1 and F2. And once we got the value of F1 and F2, we can easily get the forces in the member 1 and forces in the member 2. Static equilibrium principle can be used to calculate the forces and deflection. Static equilibrium principle. This is the static equilibrium principle. Sigma fx is equal to 0 and sigma fy is equal to 0. I have already explained you. Now, there is a third example. Is shown in the figure. Here, three members are jointed at the bottom portion and top. These are hinged at fixedly hinged. Now, it is shown that force F is applied in the vertically downward direction. The displacement in the member is delta x in the x direction, and we assume displacement in the y is delta y in the y direction. Now, how we will solve these equations? Let's first we figure out the force in member 1 is. First thing is should be comes in mind is what is the unknowns. If we know what is the unknowns, then it is easy to solve the equation. First in force in member 1 is F1. Force in member 2 is F2. Force in member 3 is F3. Now, static equilibrium equations are insufficient to solve for forces and displacement. The word insufficient. Why insufficient? Because what we have here, sigma fx equal to 0. Second equation, sigma Fy equal to 0. So we have two equation of equilibrium. First is sigma fx equal to 0. Second is sigma fy equal to 0. But the problem we have three unknown. F1, first unknown. Second unknown is F2. Third unknown is F3. So by having two equation of equilibrium, we are having three unknowns. So we can't solve this equation of so we can't analyze this structure by just static equilibrium equations. So here, this is known as the statically indeterminate structure. The structure third is known as the statically indeterminate structure. So we can't solve by just static equilibrium principles this equation. So we need to have some idea of the deflections of the structure in order to solve this structure, in order to analyze this structure. Now, in the later part, I will explain you how to solve these kinds of equation by using the Castigliano theorems or by using the energy methods. Let's move on to next part. I'm talking about statically indeterminate structure, statically determinate structure. So the first question comes in mind is what is statically indeterminate structure? The first question is easily comes to the mind is what is statically determinate structure? So the basic theory behind the statically determinate structure is that if we can analyze the equation by just by just using the equation of equilibrium. What is the equation of equilibrium? I have already explained. Sigma fx is equal to 0, sigma fy is equal to 0, and sigma fz is equal to 0. If by using these three equations we can have a solution of the structure or we can analyze the structure, then the structure is known as a statically determinate structure. But if we can't solve this structure by just using sigma fx is equal to 0, sigma fy is equal to 0, and sigma fz is equal to 0, then the structure is known as statically indeterminate structure. Now, this is the first structure. If I have given you this example, then how will you find whether this structure is statically, how will you find whether this structure is a statically determinate structure or this structure is a statically indeterminate structure? So, as you have gone through yesterday, I'm talking about structure analysis courses in the demo class. So, I am just talking about basics of statistical structural determinate structures. So you are saying me that you have a good knowledge about the basics. So you have also heard that it is a truss structure. Truss. Because first, why it is a truss structure? Because these are the hinges are given at every joint. So hinges are given at every joint, so it is a truss structure. Now, for truss structure, if structure is statically determinate, then the degree of static indeterminacy (DSI) should be equal to 0. If structure is statically indeterminate structure, then the DSI degree of static indeterminacy is not equal to 0. This is the fundamental basis of defining whether a structure is indeterminate or determinate. Now, for truss structure, we know the formula is M plus R minus 2J equal to 0. Where what is M? M is the number of members in the structure. R is the given fixed and conditions, the given free and conditions, given fixed and condition. What is the support condition is given? What are their kinematic indeterminacy? This is the value of R. And J. J is the joints. Number of joint in the structure. So let me count the number of members. So this is first member, this is second member, this is third member, this is fourth member, This is fifth member, this is sixth member, and this is seventh member. So number of members are 7 plus R. This is a hinge support. So R value is 2 for this. This is the free support. So R value is 1 for this. So R value is 3. Now number of joints 1, 2, 3, 4, and 5. Number of joints is first, second, third, fourth, 5. So 2 into 5 equal to 0. So the structure is statically determined. Same scenario in this case if we go through. Now same scenario is this. Here the value of R is not equal to 1, it is equal to 2. So M plus R minus 2J. Number of members are same 7. R value is 2 for this one and 2 for this one. Because in support, why I'm saying the value is 2? Because sigma fx is restrained, fy is restrained, but only the moment is allowed. At a hinge support, we know that only moment is allowed. So the number of unknowns that are restrained is equal to R. So in this case, sigma fx is 1 and sigma fy is 2. So the value of R is 2. Why 1 here? Here fx is allowed because the roller support is given. It is movable in x direction. And the movement is allowed because it's a hinge roller. Now the sigma fx fy is only restrained, so the value of R is 1. Here 2 for this one because it is hinge support. Fx and fy is restrained. Same condition is there. Fx and fy is restrained. The value of R is 4. Minus 2 into same 5, that is not equal to 0. So the structure is statically indeterminate structure. Now, so the first things comes in mind whether a structure is determinate or indeterminate. You just have to calculate the value of DSI, whether it is equal to 0 or whether it is not equal to 0. In your basic structure analysis, you have read these kinds of formulas uh, to determine the statically determinate structure or not. If you have doubts in these formulas, you can contact me through the Meet Your Own Teachers group, and I will ready to explain these formulas also. But at this stage, I am thinking by discussing with you yesterday, you are saying you have a good knowledge, you have a basic understanding of structural analysis. So I am thinking you know about these formulas. If you have any query related to these formulas, we will discuss in the further classes. No issues for me. Now, strain energy. What is strain energy? If work is performed slowly by the force applied to a structure, that work is converted to the strain energy. What is means by this? So, the structural engineering is a very simple engineering. Not there are only the thing is there are concept. If you have a good understanding on concept, then it is very easy subject. So what is this saying then? If work is performed slowly by the force applied to the structure, that work is converted to strain energy. Means if we applied a force P to any structure, applied a force P to any structure, then the work done by the force P is converted to the strain energy. Strain energy is defined as the energy stored in a structure due to the creation of strains. Now, first question comes in mind, how the creation of strains take place, how the deformation of the strain take place. So if we applied a force P to any structure, then it will deflect downward. It is clearly shown that it will deflect a little bit downward. So there will be a deformation in the structure, there will be the generation of strains in the structure. That's why we can say that Strain energy is defined as the energy stored in the structure due to the creation of strain. So, due to the creation or due to the formation of this structure, some strain energy is stored in this. Now, first task is strain energy, calculation of strain energy due to direct load. Direct load means this is a rod member, area A, length L, and direct in tensile force of P is applied to this structure, and the deformation is X. So work done during a small extension of dx. What is the dx? What we can say? Let me assume that due to the force P, the member deflect a distance of dx. Now, okay. So work done is equal to work done is equal to force into displacement delta. Force it's and I can write it little bit clearly for you one more time. Work done is equal to force F into delta deflection. This is the basic theorem you have read in your school days. Work done is equal to force into displacement. So here force is P, displacement force is P, F is P, displacement delta is equal to dx. So force is equal to P into dx. Now, if we need to find out the total strain energy due to the deflection delta, due to the deflection ds, then we need to integrate the equation force Fp into dx from 0 to x naught. P work done. What is saying that work is converted to strain energy. So P into dx is W. It is converted to the strain energy for a distance of 0 to x naught. So if we integrate this, then P comes out. Dx integration is x and limits 0 to x naught. So the deflection will become P naught x naught by 2. This is our strain energy stored in this rod after a displacement of dx. Total strain energy is P naught x naught by 2. They are simple mathematical formulations for the different formulas of strain energy. Now I will explain. If we divide and multiply this equation P naught x naught by 2 by A and L, what we will get? Half P naught x naught. It is same. Multiply by AL and divide by AL. P naught by A. What is P naught by? You have read in solid mechanics course. It is equal to sigma stress. Force upon area is equal to stress. P naught by A is sigma. X naught by L. What is X naught? It is the deformation. L is the total length of the member. It is equal to the epsilon. That is strain. Why? Because deflection per unit length of the member is known as the strain. We have already read in solid mechanics course. If you have doubt, I will further explain you these concepts to you. But these are the basic terminologies that you have already read in your solid mechanics course. So this term is become sigma. This term is become epsilon. And area into length. You all know that area into length is equal to volume. So what is our equation? Half sigma into epsilon into volume. Now, what we will do? Epsilon. You also know that Hooke's law. Hooke's law. What it states that stress sigma in an elastic isotropic homogeneous prismatic member. What I am saying that who stress in any elastic isotropic homogeneous prismatic member is equal to Young modulus E into epsilon sigma. The the limit, the condition for the Hooke's law is states that it should valid in only the members which have isotropic, homogeneous, and prismatic in nature. So epsilon, what we can see that epsilon value of epsilon will be from this equation is sigma by E. So sigma by E into volume. So what is equation is become sigma square upon 2E into volume, energy of strain energy. So if this is the strain energy, if we divide this strain energy by volume, that volume comes to this side, left hand side. So what is it will become? Strain energy per unit volume is equal to sigma square upon 2E. What is means that this is called as a resilience. That strain energy stored in any member per unit its volume is known as resilience, and that is equal to sigma square upon 2E. So what is resilience? Strain energy stored in any member per unit volume. So there is an importance of per unit volume, that their strain energy stored in any member or in any structure per unit volume is known as resilience. And I have make you derive that formula for resilience is sigma square upon 2E. And how it will come? If the volume, if we take it into the left hand side, U upon volume is equal to sigma square upon 2E. So U upon volume is known as strain energy per unit volume. Now, strain energy in a small beam element. This is the beam element. Force P, axial force is applied in both direction, P here and P there also. The deflection of the beam is delta x at a distance of x from the bottom. Now we have the equation sigma square upon 2E into volume. This is our equation. At each and every case, we will use this equation sigma square upon 2. So delta U will be sigma square upon 2E area into dx, because the deflection is dx. Now, if we multiply area on top as in the numerator as well as in the denominator, what we will get? Half sigma square upon AE into A square dx. And sigma by A is equal to P square by A. P by A. So sigma square upon A square is equal to P square, and A to A is cancelled. So the final equation is comes out to be P square upon 2AE delta x. So the total strain energy in any member is equal to U is equal to P square upon 2AE into dx up to a length of 0 to L. This is the basic fundamental equation for the strain energy, and in further examples we will use this equation to determine the solution of any structure. Now we will case the different cases. We will take the different cases. First case is strain energy due to bending. See, if a member is going to a bending moment M, so how much strain energy is stored in that member due to that bending? Due to that bending, how much strain energy is stored in that member? So this is a beam given. Due to the bending moment M, there is a deflection in the member is delta x. So strain energy in a member in the beam is half m into d theta. So we have clearly seen that previous for due to the forces, strain energy is P into dx. P is force, dx is displacement. In and due to the bending case, what is the work done? M into d theta. M into theta, deflection angle. So strain energy is half into m d theta. We also know that the formula in mathematics, basic mathematics, when we have read in our 9th or 10th class, angle is equal to r upon radius. So here we have the d theta is equal to delta x divided by r. R is the radius of curvature, delta is the deflection, and theta is our angle. So we have just used this equation to find out d theta is equal to delta x by r. From the bending equation, pure bending theory you have read in your solid mechanics course. The pure bending theory gives the equation m by I is equal to E by R. Here from R, if we take the value of R, what it will come? R go this side, EI upon M will be the value of R. We need to determine the value of 1 by R. So 1 by R is value is 1 upon EI, M upon EI. So delta U will be half M into M upon EI. M into M is equal to M square upon EI. So delta U will be M into EI. So total energy stored due to the bending is equal to this m square upon 2EI into dx from length 0 to L. Okay, I think I have made you understand this. This is not so much typical, it is just easy. Later on in this slides, there are two examples are given. We will take each by each and solve the whole example. Now, there can be the bending in any member, there can be the axial force in any member, there can be a direct force in a member, or there can be torsion in a member. So due to each and every force, there are some amount of strain energy stored in that member. So now first second case is strain energy due to torsion. So this is a hollow, or we can say this is a pipe type structure is shown in this figure. The torque, this is the torque is applied in this direction, T equal to torque. The deflection of the member is delta x. Due to that torque, there's a twisting or of the member, and that twisting is known as d phi. So strain energy in a small element of bar is same case. Delta U is equal to half T into d phi. T is the torque, d phi is the angle of twist. From the torque equation of equilibrium, we know that tau T by J equals G phi by L. What is G? G is shear modulus. G is shear modulus. L is length of the member and J is the section modulus. T is the torque. So we need to determine the value of d phi. If we take d phi is equal to derivative form of phi and L, T by J equals G d phi by dx. So d phi is equal to T by upon Gj into delta x. If we put d phi value in this equation, what is this? It will become, and derivative form, the total strain energy due to the torque is U equals 0 to a T square upon 2 Jg dx. Now, strain energy due to shear force. If the shear force in the member, this is our third case. If there any shear force in the member, what will the strain energy stored? Let's say that this is the beam element shown in the figure. This is our theta. Q is equal to the shear force. Q is equal to the shear force. Due to the Q, there will be a deflection delta X, and there will be a shear deformation which is known as phi, that is given here psi. Sorry, I beg your pardon. Sorry. The shear deformation is given gamma. That is also known as shear angle. So that delta is equal to gamma into dx. From the angle equals arc upon radius formula, delta is equal to gamma into dx. Same way, strain energy in a small element of beam, delta U is equal to half into shear force into delta, the deflection, delta U, half into shear force into deflection. We know the shear force. Shear modulus G is shear modulus already explained, is equal to shear force upon shear deformation. What is shear force? Shear stress upon shear deformation. What is shear stress? Tau is shear stress. Tau is shear stress. Shear stress is equal to shear force upon area, तो Q by A into gamma. So we need to figure out the value of gamma, that will be is equal to Q upon GA. And from this equation, if we find the value of gamma, then it will be equal to gamma is equal to delta upon dx. Put it in this equation. Then what will we will get? We will get this equation. Delta is equal to Q upon GA delta x. Now put this equation in this. What we will get? Delta is equal to half Q square upon GA into delta x. So total strain energy stored due to shear force is equal to U equals integration from the limit 0 to L Q square upon 2GA dx. Castigliano theorem. Important, very important. Please focus here. It is very important equation in order to solve the equilibrium conditions. What this equation elaborates. When an elastic structure, keep the words in mind, elastic structure is deformed under the action of general system of forces and movements, the partial derivative of the total strain energy with respect to any one of the forces or couple is equal to the deflection or the rotation of the body at the point of application in the direction of force or couple. There are the forces P4, P1, Pn, P2, P3, many number of forces, similarly many number of movements, M1, M2, M2. So what this total strain energy is U. So what this for equilibrium theorem says that in any elastic structure, a general system force, the partial derivative of total strain energy with respect to any one of force or couple, with respect to any one of force or any one of couple or movement is equal to the deflection or rotation of the body, is equal to the deflection or is equal to the rotation of the body in the direction of the force of couple, in the direction n is showing the direction vector, and is showing the direction vector in the force in the direction of the force of couple. So partial derivative of the total strain energy with respect to the force in any one direction is equal to the deflection at the point of application of force with respect to the direction of force. Same way it is applied in the movement case. This is our general equation to determine the deflection. I have told you the methods to determine the strain energy. If we just differentiate that strain energy with respect to the forces, we will get the deflection or we will get the rotation by differentiating that equation with respect to movement. This is the first example is given in this slides. What is given? It is a, what is this? Fixed support. Fixed support. What is this? It is a cantilever beam because one end is hanging. So cantilever beam of length L, force or W force is applied at the corner or at the end of the beam. Due to the W force, there is deflection at a distance x of deflection of delta x. And due to that force, the vertical displacement will be delta. We assume vertical displacement due to that force will be delta. So beam is subjected to bending only. Why? Because due to that loading, the beam will go in the downward direction and this will be the deflected profile I am drawing. This will be the deflected profile of the beam due to this load. And this is the deflection delta from initial to the final position. So we need to just determine that deflection delta. So beam is subjected to bending only. So we know that strain energy stored in any member due to the bending will be U equal to m square 2 EI upon dx. That I have already explained you the derivation of this equation. U is equal to m square 2 EI upon dx. So we need to find out m. So let's we say that at a distance of x, the bending moment due to the force will be, what is bending moment? Bending moment is force into displacement. So m will be w into x. We are taking bending moment at this section. This section. We are figuring out bending moment at the section 1 1. What is the bending moment? W into x. M is equal to W into x. So what is the W square x square upon 2a from 0 to L. So W square upon 2a is constant. It will comes out of the integration. The integration of x square is equal to x cube by 3, because x की power n integration will be x की power n plus 1 upon n plus 1. So x square integration will be x cube by 3. The limit from here will be 0 to, it is, I think, wrong in your PPT. It should be L, because the length of the member is L. Please correct it. Length of the member is L, so it should be L. So the final strain energy stored in the member is W square L cube upon 6 EI. Now I need to determine the displacement of this equation from Castigliano theorem. So what Castigliano theorem says that deflection, strain energy stored in a member with strain energy with respect to the force of the movement gives the deflection of the rotation. So integrate this equation. So delta is equal to del U by dw. If I just taking the partial derivative of this with respect to the W, W is our the applied force A, then we will get the equation 2WLQ upon 6CA. This is the deformation of the equation. So what is will become WLQ upon 3EI. Now the second example. It is a very simple example. We have first taken the one member example. Now we are taking the two member example. Member 1, member 2. Member 1 is from A to B. Member 2 is from B to C. Total strain energy. Total strain energy of the system will be comprised of strain energy stored in member AB, that is member 1. Strain energy stored in member BC, that is member 2. So first we are considering the member 1, that is member AB, beam AB. So here is there is only bending occurs. What is this? A to B, length of the member is A. The force applied to the member A is P, and at a distance of x, we assume the element dx. So bending moment at a distance x is will be m is equal to force into distance at a distance x. So distance is x. The moment will be force P into distance x. So moment will be m into dx. Now we have our own equation m square 2EA upon dx. This equation will be same for any kind of structure. Any kind of structure, this equation will be same for bending case only. So strain energy in member AB is equal to integration from 0 to L m square 2EA dx. Value of m will be px. Put it px. A. L is the length of the member. So here length of the member is A. So put it A. P square x squared upon 2EA. Integration of x p square upon 2a is constant. Integration of x square dx from limit 0 to a, that will be x cube upon 3 0 to a p square upon 2a. So that will be p square a cube upon 6a. After solving this, we will get the strain energy in member AB is p square a cube upon 6a. Now we will move to second equation, second member. second member. What we will do to solve this equation? See, initial condition is given. This is, we will translate this force to at the point B. You have gone through this in your solid mechanics course. If you are transferring this force at the location P, the force is directly transferred, and the moment that will generate at the point B due to the force at A, that is P into A, force into distance, P into A. So movement it will generate in clockwise direction. This is the clockwise direction. So P into A will be the moment and P is the force in that member. So considering beam BC, this is subjected to compressive load of P and the end moment is PA creating bending. Compressive load is applied to that beam B and the moment due to that force P is equal to PA. Again, direct force is P and the direct bending moment is PA. So strain energy first is stored with respect to direct force, that is P, and then strain energy stored due to bending will be different. So UBC will be comprised of strain energy stored due to bending and the strain energy stored due to direct force. But the strain energy stored due to bending will be m square 2ei into dx. We have already read. And strain energy stored due to direct force is p square 2ae upon dx from the length 0 to L. Now, what is the value of m? M value is p into a. This is the value of m moment. P into a, put it here, p square b, a square upon 2a dx. Length of the member is b. Put it here, limits, plus p square, force is minus p. Square of pa minus p is p square 2a dx. Limits 0 to b. Integrate this. P square a square upon 2a is constant, so it will come out. What will become? Integration of dx from 0 to b. In this case, p square upon 2a is constant. It will come out. What is the left? Integration of 0 to b dx. So it will, integration of dx is x from limit 0 to b. So it will come directly b, here also b. So the strain energy stored in the member will be p square b plus 2ei plus p square b upon 2ae. So the strain energy comes from bending force p as well as from the direct force pa. Bending moment pa as well as the direct force p. Total strain energy will be strain energy due to member AB and strain energy due to member BC. That will be equal to strain energy due to direct force plus strain energy due to bending moment that I've already explained you previously. So this is the total strain energy in the member. Now we need to determine the displacement delta, this due to the member P. So what will be the displacement profile? If this is our structure, sorry, this is our structure. So due to that force P, visualize in your mind. If I applied a force P here, what will it will deflect downward, and this is the rigid joint, so it will directly shift from this. So the deflected profile will be like this. Now differentiating this total strain energy u total with respect to the unknown force P in the direction of force P, then we will get the displacement x in the direction of that force P. This is the delta we will get by differentiating the total strain energy with respect to the force P. So du upon d total upon dp is equal to delta. Now integrating this equation with respect to p, what we will get? We will get our equation delta. You can easily integrate this. P square a cube upon 6ci. What will the integration of p square? 2p. Differentiation of p square, sorry, 2p. That is, I will make you differentiation of one, only one, then you can easily solve by your hand because you need to solve this in an exam. This is our u del upon del p. All are constant, so it will come out AQ 6EI upon del P square upon del P. So what is the diffraction of P square is 2P. So 2P AQ upon 6EI, that is PAQ upon 3EI. So this is the differentiation of first equation, first member UAE is PAQ upon 3A. Similarly, you can solve it for these member BC and member force BC and member due to the force, direct force P, and due to the bending moment on the member. So what we have studied today till now. Just it is now I will explain whether I have done it correct. You can check from these slides. I will make you understand what is given in this. So after integrating the U total is total strain energy. What is U total is? U total is total strain energy. That is P square AQ upon 6CI. This is the member AB plus E square A square B upon 2A. This is the member BC due to the bending moment. And P square B upon 2A. This is the member BC due to the direct shear force. That is the compression coming on the member. So integrating or differentiating the total strain energy with respect to the given force P, we will get 2P AQ upon 6CI plus 2P A square B upon 2EI plus 2PB upon 2AE. This is our total strain energy. This is applying the Castigliano theorem in the member and differentiating the member with respect to force P, we will get the deflection in the member. So the deflection delta is equal to this. So this is our full concept of strain energy. This is our full concept of strain energy. So what you have to remember in the strain energy? First, what is statically determinate structure or statically indeterminate structure? First thing the thing should be comes in your mind is what is statically determinate or what is whether the structure is given is statically determinate or whether it is given is statically indeterminate. So it should be comes in your mind. Now you can easily solve by DSI. I have already explained. Now you know that these are the different formulas. This is given for the direct shear force. U is equal to integration of 0 to L P square upon 2A. Due to the bending, similarly, U is equal to 0 to L M square upon 2EI. Due to torsion, T square upon 2JG from 0 to L. And due to shear force, Q square upon 2GA 0 to L. These are the four formulas you need to remember. You need to think in your mind. Now, what is Castigliano theorem? If we differentiate the total strain energy U with respect to the force P, we will get the deflection in the direction of the point of application of force P. This is how one thing. If we differentiate that, for the example, when we have calculated the strain energy U. Now, if we are differentiating the strain energy with respect to W, then we will get the deflection in the direction of W. That is in the downward direction, we will get the deflection. Here we will get the deflection in the downward direction due to the W. So total strain energy will be is U and the deflection will be del U by del P. So this is the first example and this is the second example. Total strain energy in the first example, it is very simple. There is one member, it and the member the force is direct force, and due to the force the bending will be there, and the bending force we have calculated Ws, and we have just followed the normal procedure that I've explained you, and we have find out the Castigliano. From the Castigliano theorem we have determined the displacement of that equation. Same way in the second member, total strain energy of the system will be comprised of strain energy of member AB and strain energy of the member BC. In a strain energy of member AB, the force P is applied, and due to that force, bending moment will be there, and that will be equal to P into X at a distance X. So P square X square upon 2EI, this will be the bending moment. Now, from the normal procedure, we can easily calculate the forces in the member P square AQ upon 6EI. This is the strain energy. Now, for the calculating the force in member second, just transfer this force P to the point B. For transferring the force P, it will give the force P as well as it will generate a moment of length A. So P into A will be the moment in the clockwise direction, and this is the force P. This is the force P acting on the member. So direct force will be minus P, and the bending moment will be PA. Minus P because it is in compression, so we have taken this as minus. So the shear strain energy will be strain energy due to this bending force PA and strain energy due to this direct force P. So UBC will be m square upon 2EI dx plus P square upon 2AE dx. So UBC we will calculate by just normal procedure that I have already explained. UBC we will get. Now total strain energy is the summation of UAB plus UBC. UBC comprises of direct force plus the bending moment. Castigliano theorem. Now integrating this, differentiating this U with respect to the force P, we will get the deflection in the P force direction. P force in downward direction, the deflection should come in the downward direction. So del U by del Pn is equal to delta A. Integrate, differentiating this U, we will get this is our final deflection. So anyone is there? Hello.
Hello.
Am I audible? Hello.
Yes.
So today I have covered the first PPT and the topic name is